Our next speaker, we have Professor Ludovic Pinard from the Cayenne National Graduate School of Engineering and Research Center. Dr. Pinard has his PhD, finalized his PhD at the University of Poitiers on the catalytic removal of volatile organic compounds. And he was awarded a Chair of Excellence by the Normandy region. And although he is coordinating several industrial projects, he contributed to the ZeoCat 3D on the topic of dehydroaromatization from catalyst optimization to pilot scale tests.
Thank you, Veronica, and thank you also for this kind introduction. So I would like to thank the organizing committee for giving me the opportunity to present this work done in the ZeoCat 3D project. And the title is From Biogas Dearomatization Reaction to the Tandem Catalysis Process for the Production and the Regeneration of a Liquid Organic Hydrogen Carrier. This work was done at the University of Poitiers, at the IC2CMP, and in collaboration with LCS. So, the human activities are causing an increase in greenhouse gas emission, resulting in the global temperature increase to up, to up 2.5 degrees. This value will lead to irreversible disruption in weather patterns, for instance, intense droop, heavy precipitation, coastal and river flooding, ocean acidification. All these phenomena will affect global ecosystem and human well-being. Over the past decade, numerous international conferences have taken place to tackle this current situation. The Paris Conference, the COP21 in 2015 has established itself as a milestone where genuine ambition to decarbonize the world have been raised. To limit greenhouse gases emission, it's important to change the primary energy mix. The first case of the primary energy mix, according to the commitment of the COP of the net zero emission scenario, so that the part of the natural gas is around 25%. Therefore, the natural gas is a keystone for the energy transition. This abundant, versatile alternative resource offers a great hope to fulfill this new requirement. Most natural gas, as you can see with the previous presentation, for energy purposes through a combustion process, but a small portion is converted into valuable chemicals such as aromatic compounds. However, methane is very resistant to chemical activation due to the symmetry of the molecule and the weak polarization of the CH bond. Methane is converted indirectly through the formation of syngas, through steam reforming, partial oxidation of methane, dry reforming, but the direct route is less developed. Among the direct route, you can find the partial oxidation of methane to methanol, the partial oxidation of methane to formaldehyde, oxidation coupling of methane, and also one interesting version, which is the methane dearomatization. But the dearomatization of methane allows to obtain both benzene and also with a relative high selectivity, around 70%, and also hydrogen, which is an energy carrier. But this reaction faces three hurdles: a low thermodynamical limit conversion, around at 700 degrees C, it is around 12%, a fast deactivation, 10 hours are enough to completely deactivate the catalyst, and also a high yield into naphthalene. So the question was, the first question to us is how to increase the benzene yield. The first strategy is to optimize the balance of the dearomatization catalyst, which is molybdenum, ZSM5 loaded with molybdenum. So it's important to play on the impact of the balance of these two functions, metallic and Bronsted acid size. We illustrate this figure plot the benzene yield by color. Blue corresponds to the low benzene yield, and red corresponds to a high benzene yield. So, regardless the molybdenum content, when the Bronsted acid side, the Bronsted acid side concentration is low, the bifunctional catalyst is inactive. This is because without pair and unpaired aluminum in the zeolite framework, the molybdenum oxide can anchor inside the zeolite. So in this case, molybdenum remains at the external surface. There is a very small window where the bifunctional catalyst is active. A high concentration of Bronsted acid size, and also a moderate molybdenum loading. At high molybdenum loading, there is an irreversible deactivation that occurs by amorphization. This is due to the reaction between molybdenum and aluminum. But at low molybdenum loading, deactivation occurs, but by pore blocking, by coke deposition. So in this case, in this process, the selection of well-balanced catalyst is a catalyst with around 3% of molybdenum and a silicon and aluminum ratio of 15. Another way to increase the benzene yield, it is to shape the catalyst. For that, we have different solutions: granule, pellet, extruded, on-demand monolith, foam, and also 3D printing monolith. So in this case, in the case of the 3D project, we choose to use a 3D printing monolith in order to avoid some issue during the regeneration. For example, the difficult for proper heat management and to avoid also some acceptable pressure drop, or also for this shape, the low weight of catalyst per unit volume. So the advantage of the 3D printing monolith was the 3D channel interconnect with port system. You have an efficient heat removal, you have low mechanical strength, and also ultra high variety of geometry. You have one image of the different monoliths synthesized in this project. But the more important, concerning the influence of the design, you have no influence of the design at the left scale. You obtain exactly the same property between the powder and after shaping. So this shows that this technique preserves the catalytic property during the scale-up. Now, how to increase the benzene yield? The increase of the benzene yield is possible by optimizing the process. For this purpose, it is possible to use a multi-tubular fixed bed reactor combined with methane recycling loops with associated after a separation of hydrogen with methane by using a separation membrane. This different implementation is possible to multiply the conversion in methane by 6. But there is some issue remain, such as a high selectivity into naphthalene, and also deactivation rate, always fast. After 10 hours, the deactivation of the catalyst is higher than 70%. And also the performances of the hydrogen membrane. The partial hydrogen separation is 80%. So the question concerns why the deactivation mitigation is limited. It is mainly due to the inhibition of the activated site by the reaction product. You have some after modeling of the absorption of the two products, benzene and naphthalene. You obtain that the energy absorption is very high. So it's possible to limit the strength of this absorption by add a small amount of hydrogen in the feed gas. And this presence of hydrogen can scavenge, we can reduce the absorption strength of the organic molecule on the active site. This means also that the key points on this project concern the regeneration step. It's important to develop some technology to improve the regeneration step. How to valorize naphthalene? So for that, naphthalene is a byproduct that needs to be valorized. This byproduct, if you look this product, is a potential liquid organic hydrogen carrier. Because after hydrogenation of naphthalene, decalin, which is liquid at room temperature, can carry more than 7% in mass of hydrogen. It's important to note that the reaction of hydrogenation and dehydrogenation are reversible, and they are catalyzed by the metal catalyst. Therefore, the issue of the selectivity in MDI process can be resolved by considering the naphthalene as a deactivated liquid organic hydrogen carrier. For that, therefore, you can change the process of the MDR process can be modified into a tandem catalytic process for the conversion of the biogas into a liquid organic hydrogen carrier. The implementation consists in replacing the hydrogen membrane by a catalytic hydrogenation unit, which should operate at 150 degrees C, and also at moderate pressure. In this concept, the most important thing is to completely consume the hydrogen formed during the formation of the conversion of methane into benzene and naphthalene. For this, the hydrogenation unit must be fit also by deactivate liquid organic hydrogen carrier. In conclusion, this tandem reaction converts methane into benzene and also into liquid organic hydrogen carrier. The hydrogenation unit play both the role of separation unit between methane and hydrogen, and also of the regeneration of deactivation and the LOH. Moreover, with this strategy, you can solve the problem of the storage, of the issue of the storage of hydrogen. In conclusion, the tandem catalysis process for the conversion of biogas into liquid organic hydrogen requires either the development of the stable bifunctional MDI catalyst, or other strategy to develop the regeneration unit by using, in this case, in the case of, for the transformation of light olefin, a moving bed. The second point, very important, is also the development of the stable zeolite-based hydrogenation catalyst. But for that, the condition that this hydrogenation unit must work at moderate pressure in order that the tandem process always operate at the same pressure. Thank you for your attention.
Thank you very much, Professor Pinard. I will start first with some questions if we have from our meeting room today.
Hi, Ludovic. This is for this. Thank you for the nice presentation. I have just a question. How easy is to utilize naphthalene as liquid hydrogen carrier? I mean, in terms of catalyst, temperature, feedstock. Is it easily implemented in this in the current MTA concept?
Yes. It is not the naphthalene. The LOHC, it is decalin. Decalin is liquid out of temperature. But the main problem can be naphthalene, but it's that's why it is a mix of LOHC, not a pure LOHC deactivate. It's that why in this process, we feed the regeneration unit by some other LOHC deactivate in order to have always a mix, a liquid at the end, because the more important for the transportation of this liquid organic vector, it is the state, it must be liquid. That was important to work a mix. The idea, the concept, it is add in the feed gas LOHC deactivate in order to maintain always a liquid.
Okay, thank you very much. Thank you.
Thank you for your question and answers. It seems we also have a set of questions from our online participants. What is the impact of the impurities in biogas on the process, such as CO2, O2, H2S, and siloxanes? Then, related, if you can clarify the impact of hydrogen partial pressure during the aromatization, and if you observe also some turtleline formation.
Okay, there are several questions. Concerning the pressure drop, by using a 3D catalyst, you have not a problem, you have not a pressure drop. The third question, what is the third question?
The sub-question, if you can clarify the impact of hydrogen partial pressure during the aromatization.
Do you clarify the, okay, the impact of hydrogen? Okay. Some experiment was carried out with different partial pressure of hydrogen. With up to 5% of hydrogen, you favor the desorption of product, and you improve the yield into benzene and naphthalene, and you improve the stability. You improve slightly the stability of the catalyst because you favor the desorption of the product. For the first question, what is the first question? Can you remind?
The impact of the impurities in biogas on the process.
Okay, concerning the impact of the impurity. Okay, if you have we have some result concerning CO2. The presence of CO2 up to 2% is benefic for the reaction because you can use one part of the oxygen of the decomposition of CO2 at 700 degrees C to remove one part of the coke, but from higher CO2 content, you observe a fast deactivation of the catalyst. Is that why for the treatment of the biogas, the higher content of CO2 must be lower than 2%. Concerning H2S, to overcome this problem, you will develop in the OCAS 3D some membrane, some catalyst, base of copper and zinc in order to trap H2S. And another point can be the water. Water can be detrimental to the material. It's important to limit the presence of water, because the water can link to the deelimination of the material, because the MBA reaction operate at very high temperature. So to resume, the concentration of water must be higher than only some ppm. CO2 can reach 1 or 2%, and sulfur compound must be very low.
Thank you very much for explaining. It seems that we have an additional question, also from the same participant. As a conclusion and the question, if you tolerate carbon dioxide in biogas, you produce carbon monoxide. How does it affect the hydrogenation step? Dr. Pinard.
Okay. It can be concerning the hydrogenation step, the presence of carbon monoxide can be a problem. Is that why it's important to manage this problem? It is a very good question. For the moment, I have not the reply.
Okay, thank you. Thank you very much. Any other question from the audience or addition? Yes.
However, there are several catalysts that perform very well on partial CO proc, so at low temperature. So it could be any Syria doped with copper that can convert CO and leave hydrogen unaffected. So we can remove easily the CO impurities from the final stream.
Okay.
Thank you for clarifying, Dr. Katsaros. Thank you for your presentation, Professor Pinard.
Okay, thank you. Bye.